title of this notes is Extreme Values of Functions. And the purpose of this topic is to learn about absolute extreme values, local extreme values, and how to find extreme values. Your absolute are also called global. Your local are also sometimes called relative. And what are extreme values for? They're useful for finding a maximum or a minimum. That's what we're going to focus on in this set of notes. And then eventually later in the chapter, we're going to see why finding a maximum and minimum is helpful for a process called optimization. Optimization is when you're optimizing the dimensions of an object. So it's really useful in the business world. If you want to package something in a cardboard box, how can you optimize the space in the box and still use the least amount of cardboard, saving your business money? So extreme values come from what's called the extreme value theorem. And you do have to know this theorem. So I want you to copy this text word for word. If f is continuous on a closed interval, a to b, then f has both a maximum and a minimum value on the interval. So two criteria have to be met. F must be a continuous function, and on the closed interval means that a and b are in the function. So the endpoints a and b are closed in. They're not open circles. If both of those things are true, then f has a maximum and a minimum. You're guaranteed to have a maximum and a minimum. So we're going to look at a couple sketches of how this could work. So look at this graph on the left. Here we have, this is a, and this is b. And we have our function going between a and b. It's a closed interval. There's closed endpoints here. Because the function is continuous and closed, because there's closed circles on a and b, you are guaranteed to have a maximum and a minimum somewhere on the interval. So somewhere between a and b, you have a maximum and a minimum. Now, the maximum or minimum doesn't have to necessarily be between a or b. It could happen at a or b. So that's what the second graph is showing us. Here's a, closed interval. Here's b, and f is continuous. So the two criteria are met. It's closed and it's continuous. And here we see our maximum is occurring at the end point, and our minimum is occurring at the end point. This is a, that's b. So the max and the min values could occur in between a and b or at a and b. There could also be a mixture. So that's what these last two graphs are showing. So here we have, here's a, here's b, and here's the function. It is both continuous and on the closed interval. So it meets the criteria of the extreme value theorem. So there's a maximum and a minimum. And here we see, here's the maximum in between a and b. Here's the minimum on the endpoint A. And then vice versa, we can have here's A, here's B. F is continuous. It meets the two criteria. Here's our minimum between A and B. Here's our maximum on the endpoint. So your max and your min can occur in between the endpoints or at the endpoints. So there are a couple different types of extreme values that can happen. So we have a graph here. And I want you to sketch just the blue graph to start with. Just the blue graph. So it goes up and then down and then up at this like cusp thing and then back down. So this graph starts at A and ends at B. It is closed and continuous. So it meets the criteria of the extreme value theorem, which means we are guaranteed to have a maximum and a minimum. Here we have 5 different maximums or minimums, and they're all different kinds. So at A, we have what is called an absolute minimum. It's also sometimes called a global minimum. Either of those vocabulary words is fine. You can use them interchangeably. So the absolute minimum means that there's no smaller value of the function anywhere. So on the entire graph, f, this blue line here, never goes lower than it does at A. Likewise, we have an absolute maximum over here at D. Similar definition. the value of f, that blue function, never goes up any higher than it does at d. So that's called an absolute maximum. It could also be called a global maximum. And then we have a couple of other maximum and minimums. They're not the absolute or the global. They're called local. So the first one we have is happening here at C. There's a local maximum. And it's a local maximum because if we're looking nearby, it's the maximum value nearby. Likewise here at E, we have a local minimum because there's nothing lower than it nearby. Same thing for this endpoint. This endpoint is a local minimum. There's nothing smaller than it if you're looking nearby. And so what I want you to notice is that there are multiple local minimums. There's 2 on this graph. There's no limit. For your absolute max and min, because it's the largest and the smallest, you can only have one point that is the largest or the smallest. So there's only one absolute maximum and there's only one absolute minimum, but there can be any number of locals. Any number of locals. There's no limit to how many local max or local min there are. So next we're going to talk about how to find a local max or a local min, or a global max or a global min. So just looking at this graph for a second, everywhere where there's a maximum or minimum, think about the tangent line. So if I were to draw the tangent line in for this local maximum, what I want you to notice is that it's a horizontal line. Same thing over here for this local minimum. And a horizontal line has a slope of 0. Now this maximum, it's a cusp. There is no tangent line. The cusp doesn't have a tangent line. Remember all those places that don't have a tangent line? You have a cusp or a corner or a vertical tangent. So we have no tangent here at this cusp. That's going to lead us into this idea of critical points. We're going to use critical points to find extreme values. The definition of a critical point, it's a point in the interior of the domain of a function f at which f prime equals 0 or f prime does not exist. If either of those 2 criteria happen, you have a critical point. Going back to this word interior, remember f is defined on an interval from a to b, and it's closed, which means a and b are in the domain. The interior means not counting a and b. A and b are the endpoints. So you're looking from a to b, not counting a and b. And you're looking to see where your derivative is 0 or does not exist. And we can flip back to this other picture. If my derivative is 0, I have this horizontal tangent line. Or, if my derivative doesn't exist, there is no tangent, something interesting happens there. So those are critical points. So now how do we actually find extreme values? So to find an extreme value, you're going to check 2 places. You're going to check your critical values or critical points, and you're also going to check your endpoints. Because we can see on that graph before, there were only 3 critical values. Here's 1, here's 2, here's 3. The other max and min happen at a and b at the endpoints. So we're going to check both places. Check your extreme values. To find your extreme values, check your critical points, check your endpoints. So we're going to do one example together. We want to find the absolute maximum and minimum for this function on the interval -1 to 2. So absolute maximum minimum, those are types of extreme values. The other types of extreme values are local max and min. So if I'm going to find an extreme value, I'm going to check 2 places. I'm going to check my critical points and my endpoints. So let's check critical points first. So remember, a critical point happens where your derivative is 0 or does not exist. So we're going to take this original function and we're going to check its derivative. So remember, I'm multiplying my coefficient and my power, and then I'm subtracting 1 from the power. That's our power rule for derivatives. So 2x to the negative 1/3 power, remember that a negative power means it really goes in the denominator. And a 1/3 is really the cube root. So I want to know when this thing equals 0 or does not exist. This is a fraction, and I cannot divide by 0. If you have division by 0, you don't exist. So I want to know when does that denominator equal 0, because that's going to cause division by 0. So to get x by itself, it's under the cube root, so I'm going to cube both sides to cancel out that cube root. So that'll leave me with x equals 0 to the 3rd power is 0. If x is 0, my derivative would be 2 over the cube root of 0, which would be 2 over 0, which is undefined, does not exist. So x equals 0 is a critical point. The other place I'm going to check besides my critical points are my endpoints. So this functions on the interval from -1 to 2. So I'm going to check also x equals 1 and x equals 2. And what I'm doing is I'm checking the outputs because I want to see which one is the absolute maximum, which one's the absolute minimum. So I'm going to check my critical value of 0. I'm also going to check my endpoints of -1 and -2. And I'm going to put those values back into the original function f, no longer working with the derivative, because I want to see what the outputs are. So remember, my function was 3x to the 2/3 power. So if I plug in a 0, 0 to the 2/3 power is 0, times 3 is 0. Remember, you do your exponents before your multiplication. Now I'm going to check -1. Okay, you can use a calculator here. -1 to the 2/3 power is +1, and then multiply by 3. And then lastly, I'm going to check when x is 2. So I'm putting this one into the calculator, and I'm going to get about 4.76. So these are the output values at the critical value and at the endpoints. Those are the endpoints. That's the only critical value that we found. I want to know where's the absolute maximum. So looking at my 3 outputs, which one is absolutely the largest? I can see this one here. So that tells me that at 2, I have an absolute maximum. And then looking for an absolute minimum, I want to see out of these 3, which one is absolutely the smallest, and it's this one. So that tells me this is an absolute minimum. So I'm just going to write this as a complete sentence, my answer. I'm going to write there is an absolute maximum at 2, 4.76. And an absolute minimum at 0, 0. This is going to be it for our notes. We're going to talk about finding local max or minimum when we come into class on Monday.